Hi, this video I'm going to teach you how to approximate the area underneath a curve. And we're going to use rectangles. We don't have to use rectangles or other techniques. You can use parabolic arcs, use trapezoids, you can use whatever you like. But this is what we're going to start with. So here's a basic example. And let's suppose, and we're going to keep it nice and easy for now, x squared function, and I want to approximate the area under the squared function. And under isn't always a literal under, but in this example it is, from 0 to 3. So that's the area I would like to approximate. And so we're going to approximate the area on the interval 0 to 3, or from x equals 0 to x equals 3, or from 0 to the lower bound to 3 is our upper bound. Okay. So what I'm going to do is I'm going to decide to use rectangles. You know why? Rectangles are nice and easy, and I'd rather use rectangles for now. So since I have 1, 2, 3 nice unit lengths here, I'm going to just decide that each of the bases of my rectangles will be 3. And so I'm going to take a look at my first, what I call subinterval, and I'm going to put a point here. That's called tagging, in this case the right endpoint. I'm going to move up to the function, over, and that is one rectangle. Okay, so I tagged at 1 the right endpoint of my first subinterval, tagged my right hand endpoint, went up to the function, and that determined my first rectangle. Again, kind of fancy language for a basic process, although sometimes that's what mathematics does. I'm going to take a look at my second subinterval, in this case from 1 to 2. I'm going to put a little 2 there. And so if I'm looking at that right endpoint at 1, I'm going to put a tag there, at 2. And I'm going to bonk that up to the function. That determines the height. And there's my second rectangle. Then just for argument's sake, I'm going to take this third subinterval from 2 to 3. And just to be uniform, I'm going to tag the right endpoint, which is 3. Bonk that into the function. There's my third rectangle. Now you don't have to do it this way. This is just the way that I'm deciding to do it. You can tag anywhere along each of the intervals, but it's nice, at least for organizational sake, to keep things consistent. Okay, I have a nice base for each rectangle of 1, just because I chose for it to be 1. 3 rectangles evenly partitioned about the interval 0 to 3. And I just chose to have as my heights the right endpoints of each subinterval. So I tagged 1, that's the height, tag 2, the height of my second, tag 3, height of my third. Okay? So therefore I can set up the area under the curve is approximately base times height of the first rectangle plus base times height of the second rectangle plus base times height of the third rectangle, which I'll just write like that. Again, kind of a basic idea, but I'm making it a little more confusing with language and notation. And that's going to be equal to base are all 1, just by the way in which I set it up. Here are my bases, my changes in x. 0 to 1, that's 1. 1 to 2, that's 1. 2 to 3, that's 1. Okay, now the heights are determined by plugging each of the tags, and here are the tags. Tags are x values that, when plugged into the function, determine the heights. Here are my tags, 1, 2, and 3. Those are the right endpoints. So when I square 1, I get the height of the first rectangle. When I square 2, I get the height of my second rectangle. And when I square 3, I get the height of my third rectangle. Okay, so here are my tags. I'll highlight them in yellow, 1, 2, and 3. When plugged into the function, those tags determine the heights of those rectangles. And so I'm going to get the area of my first rectangle, which is 1 times 2 squared, which is the height here, that's 4. Gives me an area of 4. And then 1 times 3 squared, which is the height here, which is 9. 1 plus 4 plus 9, there's 14 square units. Okay? In theory, to make this a better approximation, note that this is an over approximation, essentially because of this void area, this extra area up there. So the definite area underneath x squared from 0 to 3 is less than 14, I'm sure of that. So to get a better approximation, I'm just going to use more rectangles. And so let's take that same area, x squared, here's 0, and here's 3, and just to show what might happen, instead of using 3 rectangles, now I'm going to use 6 rectangles. Okay, and so just to make things easy on myself, here's 1, here's 2. Each of the rectangular bases, let's say, will be a half. So that's 1/2, that's 1, that's 1.5, which is 3 halves. That's 2. This is 2.5, which is 5 halves, and that's 3. Okay, now I'm going to create my rectangles, and I'm going to tag the right endpoint of each subinterval. So the first subinterval from 0 to 1/2, I'm going to tag the right endpoint. Second subinterval, 1/2 to 1, tag 3 halves, tag 2, tag 5 halves, tag 3. Now why did I tag these? Because those tags get thrown into the function to give me the height of each rectangle. The nth tag into the function determines the height of the nth rectangle. Okay, and so what we have here is the area will be approximately the sum of, I'm using a little sigma notation, the sum of from 1, in this case, to 6 of all the bases, b sub 1s, times the heights. Okay, and since each of the bases is 1/2, here are the bases. Okay, the length of each base of the rectangle, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. Each of the bases is the same as 1/2. I can actually pull that out, which is going to be 1/2 times the sum of the heights. Okay, well, what are the heights? The heights are each of the tags plugged into the squared function, using the right endpoint in this case. Notation. So 1/2 squared is the height of the first rectangle, plus 1 squared is the height of the second rectangle, plus 3/2 squared is the height of the third rectangle, plus 2 squared is the height of the fourth rectangle, plus 5/2 squared, which is the height of the fifth rectangle. I'm just coloring them in to keep track. And plus 3 squared, which is the height of the sixth rectangle. Okay, and if I calculate that sum, I will get a better approximation of the area. So let's say it's 1/2 times 1/4, which is 1/2 squared, plus 1, plus 3/2 squared, which is 9/4, plus 4, plus 25/4, plus 9. Okay, I'm going to combine my like terms. I get a 1. Well, they're all like, but my nice positive integer terms. 1 and 9 and 4. So it's going to be 1/2 times whatever's left in the parentheses. 1, 9, 4, that's 14. Plus, I got some halves to consider too. And those halves, fourths rather, 1/4, 9/4, 25/4. Let's see. 1 plus 9 is 10, so that's 35/4. And I'm going to multiply that by 1/2. So let's get a common denom for that 14. So I'm going to change 14 into how many fourths it is. And so I'm going to call 14 times 4, which is 64, I believe. 56 fourths. And 56 plus 35 is going to be 91 fourths. And I multiply that one by 1/2, it's 91 eighths. Which is, let's see, 1 and 3/8. Okay, so that's a better approximation, 11 3/8, than the original 14. Okay, still an over approximation because of the void area, because it's concave up, and I'm using the right endpoint technique. I'm tagging, the right endpoint. They're my kids. Okay, but nonetheless a better technique. So using 3 rectangles, I get more excess. I get a 14 approximation. Using 6 rectangles, I have less excess area, and I get a better approximation. So in theory, the more rectangles you use, the closer approximation we're going to get. You smell a limit coming? I do. Hang tight for the next video. Bye-bye.